Okay, let's get started. Today is the second class we'll have. Hesitated, like, is it going to be a lecture or problem solving? We're going to try to solve some problems in class today, so we get some of the practice that's required to get some of these calculations under our belts, the ability to do it. So you guys will probably work with somebody next to you at some point. We'll just kind of see how this goes. And raise your hand if you studied some of this stuff. You feel like, okay, that helped a little bit. Few of you. That's really, really important to go ahead and dig in there and try some of these calculations. So we're backing up a little bit. We're gonna look at one of the calculations that we did last class so that we get it warmed up, and then we'll move forward with some new examples. So the big picture is that if we have chemistry, I'll just write a random equation up here. Recall that these are mole quantities, these coefficients. So they're numbers, numerical basis, not mass quantities. And we're stuck in the mass world is how I like to think of it. Like, wait a minute, I can use a graduated cylinder to measure a volume of a liquid. And if I know the density of the liquid, I can calculate what the mass of the liquid is. And then I can, okay, now I know how much material I have in my hands. But then I use the mole concept to translate that to these numerical values that appear in these equations. And these are just ratios, recipes. One thing becomes one other thing and three other things. That's all that means right there. So when we look at a balanced equation, or maybe even an unbalanced equation, here's an unbalanced equation, I think. So the first thing is to always balance your equations. And if we get a question like, how many grams of such and such, boom, bell goes off in your head and you say, well, the first thing I'm going to have to do, almost certainly, with almost all chemistry problems of the stoichiometry problems, you'll convert from mass quantities to mole quantities. Then you're in the world of the equation. Once you're in the world of the equation, you can cruise back and forth using mole ratios, and then at the very end, extract yourself from the paper chemistry back to the lab to balance the graduated cylinder by calculating from moles to gram quantities. That's a really rough, like usually that's the pattern. That's usually what we do. So instead of walking you through the solution and you sitting there listening to it, let's just do this problem. Let's go ahead and work with somebody next to you. And instead of necessarily doing the math, let's first map the solution. So you can collaborate with anybody that you want. You can also work alone if you prefer. Whatever's most effective. Do what's effective. So the first thing that I would like to see is a series of steps. And my personal habit is this kind of thing. And it's just a little clue, this is what I do with all these problems. I'll circle a step. So the first thing would be balance the equation, for example. And that's just what I do. But figure out your own way. Sure, I suggest you try it if you don't have a... What's that? You got to balance the stupid thing. Oh, I think it's already done,
Yeah,
but
it is.
that's okay. We're, you know, yeah, I know it's up there, but you need the molar mass. So don't uh, do yourself a favor and don't just buy that 152 grams per mole. Stop and say, wait a minute, how is that calculated? Let me calculate it. Let me practice it. Let me make sure the units are correct. Let me observe the units of molar mass are always grams per mole. It's not gram quantities, it's grams per mole.
Okay, so you have two of those. Plus 3 oxygen. And then not technically more mass.
I think we're going to do the other. Oh yeah, there's two.
Like that. It's 152. Find out how we got that.
Oh yeah, so take two of those.
See if it's calculated.
No. The one day I didn't bring it.
51. Can we just round that? 52. 52.
I normally always bring it.
Oh, what I rounded?
Yeah. Oh. I haven't done an oxygen like that.
Now for this. We've got two more there. So we do that 2 times. And then do that 3 times.
Yep.
That I'm counting.
So that I bet you that's right because it's close.
What were you doing?
Oh, I was going to. Number of currently that's not right. Because there's two of them. In the end.
Yeah.
There's like two of them.
Yeah. I think we just have to know the more mass of that and then times that. Like, you know what I mean? What are we trying to get?
Oh, yeah. Because it's two of those two together.
Yeah, okay. But it's kind of confusing when you have to predict what comes out. Or with the precipitates. I don't know which one's gonna form a solid out of the two.
Solubility tables in your book?
I know.
Yeah.
She gave me one of those sheets.
Yep, you free to use any
Do we need to
resources you
memorize
need.
that?
What's that? No.
Okay, thank goodness. She's like,
What
well, you
page
better
is it
ask.
on?
What page is it on? I don't have that in my head, but you can find it in your book. And there are other resources available on the web, solubility tables.
She has one at the health lab.
Math lab?
Okay, let's have a look at this. What are the things that I look at? See this balanced equation? For me personally, I ask myself, with this question, is it relevant that this is solid phase, this is gas phase, and this is solid phase? Is that relevant? It's information that's maybe important in certain situations, but for this question, we aren't being asked anything about the physical state of the reactants or the products. So when I rewrite the equation, and yes, I do rewrite the equation, I don't stare, I rewrite things and I say, well, wait a minute, here's a pared down version. It's a little bit simpler to look at here. And sometimes just removing things that aren't relevant to the problem is part of the solution. It's like, okay, we don't need to put this as solid gas and solid here. The second thing I do that I showed the other day is I write down below, or maybe even above is better. I've summarized the problem. I know this chromium in gram quantities. I know that I have excess oxygen here, and I'm asked how many grams of this chromium oxide, this chromium 3 oxide that I have. So now I've reformulated the word problem into a little, boom, this thing. Makes it easier. First step is to balance. What was the second step? Determine molar mass. And what did you do then?
Convert the grams of
Convert what?
the chromium
Grams chromium to what?
moles.
Moles. Fourth step was what?
Convert moles chromium to moles of chromium oxide.
Yeah, we skipped.
Fifth step is what? Moles, convert moles chromium oxide to grams chromium oxide. Okay. And chromium oxide, that's a type 2 compound, right? So recall, how do we name chromium whatever oxide? That chromium has an oxidation state of +3. It has a charge of +3. So it's chromium 3 oxide is the full proper name of that compound. So let's look at each of these steps. They are all the same sort of math. They're conversion, they're ratios, using ratios to convert from one set of units to another. So realize that if you have trouble, like, wait a minute, you have trouble with one type of step, once you get it down, they're all very, very similar. And so that map, that idea of going from one stone to another as we jump across a stream, that's what we just did here. So each of those steps, boom, they're almost in the can. They're pretty simple math. And you just string them together and you have your solution. Any questions about this problem? We'll show the full solution typed out. It's posted on the web. Any questions about the logic? Notice we're doing exactly as we described at the beginning of the class. This step is the conversion from the world that we're in, our 15-gram quantities, to the mole quantities. And really it's two steps. First, we have to calculate the molar mass. How do you do that? somebody blurt out real quick, how do we know the molar mass of that compound? Yeah, you take the number of moles of each element that's a constituent element of the compound, and you multiply the molar mass of each element, you add them up, and that's the molar mass of the compound. You'll have to calculate molar mass in your sleep by the end of this course. So you'll just be doing that boom, boom, boom regularly. And that's kind of good news, because on the final, I don't have to, you'll be surprised if you learn these basic steps, you'll be surprised how, oh, wow, that's all there was to chemistry, really. There isn't a ton of things to know. It's just that some of the things are kind of difficult. So realize if I learn that, that's going to be on the final. That nothing that we're doing is sort of a waste of your time. Converting chromium, the gram quantities to moles, that's a mole ratio sort of, or excuse me, how do we do that? Let's just do it. We have 15 grams of what? Chromium. And we're going to multiply that by what? The molar mass? Oh, somebody says, no. I don't want to multiply. What are you going to multiply? To convert this mass quantity to moles, what do we need to multiply? 1 mole equals well, it's true that it equals 1 mole of that chromium does in essence equal 152 grams. What's that? Oh, I'm sorry. 52 grams per mole chromium? Yeah, okay. So it does equal 1 mole, but it's a little better to say, wait a minute, per mole we have 52 grams. So a fraction is 1 mole per 52 grams. An equivalent and reciprocal ratio is 52 grams per 1 mole. And that second one is the molar mass. Notice that our units cancel and we're given units of moles. That's critical. Don't even get out your calculator until you check your units and say, okay, now I'm ready to punch some buttons. Don't worry about the numbers as much. Fret to no extent about your units. You can't be overly concerned with your units. Just like go crazy on your units. Like just swarm all over your units and forget about the numbers for a second. What is the number? Yeah, like flies on a rib roast. Just do your units thing. Sorry. Got this vision. Never had my rib roast. There's flies all over my rib roast. All right, what's the number? 0.289. Okay, she's got 3 sig figs in that number. Notice I said 0.298, as I'll be barking at you in the lab to always say 0.298, because that's what we do as chemists to keep track of that decimal point. It might seem sort of redundant or ridiculous to always say 0.298, but we do. We use that zero. There are 3 sig figs here. Oh, okay. The problem had 3 significant figures here. There's only 2 here, the way we reported it, but I'll bet on your periodic table you have it out to at least 3. So yeah, that's 3 significant figures. The whole problem is nothing but a series of those types of calculations. So here's a calculation. Here's another one. We just did this one. Notice 0.288 is a little different from our 0.289 that we got. That just comes out of the fact that you used a slightly different molar mass for chromium. Maybe it wasn't reported by the same people. Those are minor sort of concerns, but they bring up the idea that, yeah, all these calculations are estimations. This is the calculation we just did. Here's the next one. What is this? I mean, what's the story with that? The molar ratio, where does it come from? the balanced equation, right? Yeah. So it's only the balanced equation that gives you that proper mole ratio. But look again at the units. The mole ratio, those moles have to cancel properly in order to retrieve out of the calculation the number of moles of chromium 3 oxide we get out of the problem. Yeah, question.
So where did you get the 15 grams?
The 15 grams was given.
Oh, okay.
So
I missed that.
if we go back to the problem, that's right there.
Oh, okay.
And that's why if I'm sitting here reading and rereading this sentence, that's just a pain in the neck. That just causes you time. Go ahead and scratch those given quantities below or above the equation and stick in there a big question mark. What am I trying to do here? Okay. Any questions about this calculation? Here's the very last step. This is converting from moles to grams of product. And here's the so-called conversion string that just makes me twitch with displeasure. But I'm the only guy on the planet. Well, no, not really the only person. Well, I would say teachers of chemistry are split 50-50. Chemists just look at it and say, why would you want to confuse yourself by stringing everything together? But there's a big debate about it. So if you've learned this, it does in fact work, but yeah. So here's another one. Here's the so-called conversion string. Let's do one more. Notice how much time we burned up. We burned up about, let's just call it doing this, maybe 10 minutes per problem. After you get practiced up, it'll take you about 5 minutes at least for a problem. You have 20 problems on an exam, 20 times 5 is what, 100 minutes? But that doesn't fit, so yeah. Some chemistry problems take 20 minutes to solve even when you know exactly what you're doing, even when you're marching through it like walking down the hallway. So be patient with the idea. Don't give up after 5 minutes and say, oh man, I can't do this. I don't know what I'm doing. It's not going to work. So here's another one. Let's do this one. And yeah, the solution's there, but I don't care about that. Let's just look at it, do it with your partner. Punch it out, see what we can do. Use the exact same method we just described.
Do we round up the numbers when we find the molar mass from on here? If it's like 51.9, and you say it's 52.
51.9. If you rounded 51.9 to 52, and you ran that all the way through your calculations, that's a perfectly legitimate thing that a scientist would do. Like, okay, wait a minute, I need more significant figures, so I'm going to go back and I'm going to do this without rounding. So the question, yeah, do I round or not? Or, I mean, here I have the molar mass to 4 significant figures. Do I need that or not? The answer is, if you round it at the beginning because you were just making an estimate, and you do all your chemistry correctly, and you come out with 1 or 2 sig figs, and the other person next to you didn't round and they have 3 or 4, both people are doing good chemistry.
Hydrogen fluoride.
Okay, so I have a question.
Yeah.
If I did this far, I don't know what to find the molar mass of this. Because I balanced it and I put down what I know. I have to define molar mass. I don't know. You know what I'm talking about?
Maybe, but not sure. So let me
Okay.
work it. So
I'm kind of confused.
yeah, let's have a look at this. So here is the reaction. I did the same thing I did before. I dropped those physical states. It's not that they're not important, but for this problem, they're not important. So I got that garbage out of my way. Is it balanced? Yeah, so we check if it's balanced. And then I do this type of thing that I did before. We're trying to figure out how many grams of tin fluoride we're going to get out of these amounts of starting materials, or reactants we would call them typically. Plenty. The problem says plenty. Chemists would usually say we have excess, but plenty is for like, okay, we got more than we need. So we don't have to worry about the amount of tin limiting the amount of product we get. So let's do a slightly different sort of way of thinking about how we're going to solve the problem. Here's our starting point, and our finishing point is grams of tin fluoride, right? So now we got to do this skippy deal across the stream. We got to figure out what the steps are. It turns out with this one, they're the same as the last problem. So don't worry about how to do something first. Worry about what you need to do and then how at each step. So it's like, okay, wait a minute. We're in the gram world. We have to go into the mole world. Moles of, what is it again? Hydrogen fluoride. Then we're going to convert to moles of tin fluoride, and then we're going to convert from that to grams of the tin fluoride product. 1, 2, 3 calculations, except we do need molar masses. And somebody had a question about, I'm a little confused about molar masses. Tin fluoride, we might need the molar mass of that, but we definitely need hydrofluoric acid, the molar mass. What is that?
20. I got like 19.99.
Oh, controversy breaks out in the chemistry class. You got 20, wait a minute, you got 20, I'm so 20.008 what?
Grams.
Oh, not chickens, I guess. Gram. Okay. Grams?
Per mole.
Oh, got it. Okay. Now I'm a little calmed down. I was getting grams per mole. Is that correctly calculated, or somebody said 19 something?
Well, yeah, I use this, but the screen says that. So.
The screen. And the screen always tells, it's like the internet, right? If you read it on the web, it's got to be true. Did the screen lie? The screen isn't up here. The only screen I see now is this. Let's assume there's no mistake. Mistakes are different from not knowing how to do it. Mistakes are more you should have more patience with math mistakes. We always make those. And you can get rid of them by rechecking your math. But not understanding how it works, that's the one we got to address. Yeah.
So you got that number by adding the weight of hydrogen and the weight of fluorine?
Yeah, exactly. Atomic weight, atomic mass, molar mass, those are interchangeable terms. We kind of throw those around. Maybe it's a little bit sloppy to do that, but the atomic weight or the molar mass of each of those constituent elements would give us the molar mass of that compound, giving, again, all the units. Then the mole ratio. This is what we use the mole ratio that's characteristic, again, of this balanced equation to go from here to here. And then we use molar mass again, but this time with a different compound to go from the number of moles to the number of grams. Any questions?
And the mole ratio is, you know that by the coefficients of the.
Yep. Let's write down the mole ratio. So to convert from moles of HF to moles of tin fluoride, we're going to have to know the relationship between those two chemicals. So it's 2 moles HF per 1 mole of tin fluoride. That's a mole ratio that we use to make this conversion. And maybe we'll use that version or the reciprocal, but they both hold for that balanced equation. Okay. Unfortunately, we have to move on. That stuff is required to do the to take into consideration things like limiting reagent more carefully. So, that's why I stopped and said, wait a minute, we've spent 35 minutes thinking about this again. The next stuff, there are more examples here, and we're reviewing a little bit with stoichiometric ratios, but we're going to go on to, wait a minute, what about theoretical yield and limiting reagent things? So the stoichiometric ratio is a ratio that's characteristic of the balanced equation. So if I say, I'm going to run this reaction with a stoichiometric ratio, it would be 1 mole of nitrogen for 3 moles of hydrogen. And if the reaction went perfectly, I would get 2 moles of ammonia in this case. And that's stoichiometry. It never works out quite that way because maybe you have a whole bunch of one reactant, you don't have much of the other, and the second one is really expensive. Maybe it's, say, platinum or something, and you're running a reaction. You want to use up all your platinum, so you'll do what we call whale in one of the reactants. That's slang, and chemists always say that. Yeah, let's whale in the nitrogen because the hydrogen's more expensive. We want to suck up all the hydrogen. So if you do that, you're left with some nitrogen, like depicted in this cartoon here. It can be a good thing. And then maybe you can just get rid of the excess nitrogen and you've used up all your hydrogen. So there's never, we typically, we can't, in theory, mix the reactants in perfect stoichiometric ratios. There's essentially always a limiting reagent or a limiting reactant, and we have to carefully consider this because we want to know how much we're going to get out of the reaction. And so there's one that runs out completely. It gets all used up because the other one is present in excess, and the one that gets completely used up is the limiting reagent. It dictates how much product you can get out of it. If you anybody in here run a bicycle factory? Like nobody. Okay, excellent. So she's got a bicycle factory, and as she's got all these people working in this bicycle factory, and there's some people that are making seats, some people are making frames, some people are assembling wheels. If you think about the bicycle factory, you could write down a chemical equation for making bicycles. It's 1 seat, And I don't want to get too distracted here, but let's do the bicycle thing real quick. Let's take, we've got seats, we've got wheels, and we have a frame. Let's just call that our bicycle. Seats plus wheels plus frames equals bikes. Balance the equation. That's all the chemistry is. One seat, two wheels, one frame makes one bike. That equation is balanced. It's an assembly line. The atoms are going together in the same way the bicycle goes together. You know, they're assembling or combining on a numerical basis. So what happens if she has 87 seats, 16 wheels, and 4 frames? How many bicycles can we make? 4?
Yeah.
Wow, that took you like what? Not even a second to answer that. Why is that easier than chemistry? Well, okay, our limiting, you glanced up there, you said, wait a minute, we've got 4 frames. So did anybody calculate how many wheels you're gonna need? You just hook, line, and sinker thought, all right, we got 4 frames, we can make 4 bikes. Well, how many wheels do we need? We need 8 wheels. How many seats do we need? 4. How many seats do we have left over when we're done? How many wheels do we have left over when we're done? How many frames do we have left over when we're done? How many bikes do we have? 4 bikes. It's that easy. It's like, wait a minute. The frames were the limiting reagent here. Excess wheels, excess seats, huge excess of seats. Her seat people are super efficient at making seats, and they just keep churning these out like those, what are those? Anybody ever see Willy Wonka's Chocolate Factory?
Yes.
Those weird little dudes that are colored that are all Oompa Loompas, yeah. So the Oompa Loompas are just churning out these seats. The slackers in the factory are the frames. So she's going down there every day barking at the people. Wait a minute, you guys are limiting the output of my chemical reaction. You're not making enough frames, therefore this other stuff is in excess. The frames limit the output. The chemistry is exactly the same situation. These are chemicals that have little subscripts and physical phases and all that, and that's a distraction to you. You quickly, in less than a second, came out with, I think we can make 4 bikes. So we have these procedures that once you practice up, you know, oh yeah, it's just the same thing as making muffins. If you look in the refrigerator and you need 2 eggs per dozen to make the muffins, and you see 3 eggs, boom. I cannot double the recipe. I can't. And you do this every day. Chemistry is the same thing. Exactly the same situation. There's leftover stuff. With the bicycles, we calculated we're going to have 83 seats left over. With the chemicals, it's the same thing, except instead of bicycle seats, it's moles of reactant A, and it's just all a big fog in there. It's like, wait a minute, that's a distraction. But if you equate moles with numbers of objects and settle into the idea that the chemical formulas represent real things, then it's like doing the bicycle thing. We could do this calculation. It would take probably 10 minutes or 5 minutes or whatever, but we could do this based on the same sort of, let's hesitate here. Like, wait a minute, what is this? How many grams of ammonia are produced from the mixture? 3 grams of each of nitrogen and hydrogen. Like, ooh, it's a problem. By that, I mean, it's not an exercise, it's a chemistry problem. So if you don't know how to solve it at first, turns out you're a hominid trying to do chemistry. Like, oh, okay, that's what happens when we have a problem. We got to think about it. What would you do as a first step? as one of the great apes solving chemistry problems. Actually, we're the only ones that can do it. That's kind of cool. So you think it's a drag to have to solve chemistry problems? So the other great apes think, oh God, you guys get to solve chemistry. We can't even do it. Look at this. What do? What's your first step?
Convert the grams of nitrogen.
Yeah, I'm really gripped about this whole gram quantity thing while I stare at a balanced equation. Same thing again, we convert to moles, but now it's a different problem, but the same concepts apply. We've got a mass of this and a mass of this, and it turns out we got to convert both to moles to figure out which is the limiting reagent. So hydrogen has a molar mass of what? Yeah, I was vague in that. Hydrogen gas. What's the molar mass of hydrogen gas? Diatomic hydrogen gas. It's 2 times the molar mass of hydrogen, the element, right? Two of these atoms are bonded to one another. So 2 grams per mole here. Nitrogen gas. Nitrogen is also a diatomic element. What's the molar mass of nitrogen? Gas. 28-ish. So we have 28 and we have 2. We have the same mass of each of these chemicals. These are the peanut M&Ms. These are the regular M&Ms. Yet we have the same mass. When you buy that bag of M&Ms, same mass, you get a lot more of the little M&Ms than you do with big M&Ms. The mole quantity of hydrogen is far greater than the mole quantity of nitrogen here. So which one's going to limit is, oh, but wait a minute, there's a mole ratio we have to factor in here. The problem uses exactly the same concepts that we've already addressed, but they're formulated slightly differently. So that's an important point, that wait a minute, it looks different, but the same concepts apply. So each of those conversion steps you assemble in different ways every time you get a different chemistry problem. New concept, totally new, haven't mentioned it at all. If you do a chemical reaction, okay, back to the bicycle factory, it turns out that her employees are even worse than we thought. These Oompa Loompa people, I guess they're people, they're working in the factory and they're hacks. It turns out they made 4 bicycles, but some schmo Oompa Loompa damaged one of the bicycles on the way out of the factory, and they decided to throw that one in the dumpster so they don't get fired. 3 bicycles come out of the factory. When she calculates, wait a minute, based on our starting materials, we should have gotten 4 bicycles. The actual yield of bicycles is 3. The theoretical yield is the amount that you would expect based on the amount of starting materials. Theoretical yield and actual yield are never the same in chemistry. There's always a bicycle that gets damaged on the way out of the reaction, so to speak. So the percent yield is the ratio of these things. The theoretical yield, you calculate that based on your paper chemistry, the type of thing we've just done. But the actual yield is how much you get out of the reaction. The stuff that you carry over to the balance, you stick on the balance and say, you know, theoretically, we should have gotten X number of moles, which is equivalent to 1.8 grams. But we only got 1.6 grams out of this. So the percent yield is actual divided by theoretical. Easy calculation to do once you get the idea. You know, when you make the muffins, and there's always somebody in your family that's like going after that bowl that's sitting in the sink, because they get out the spatula and they're like, nah, I gotta get the residual stuff out of there. That's my favorite part of the, you know, and they're like licking the thing, and then another person in your family starts yelling at them, get away from there, get him out. I'm not sure why they do that because it's pretty efficient. In chemistry, where the same thing happens, you do a reaction in a reaction vessel and you try to pour the stuff out into another vessel and some of it stays. And so you lose material. So the actual yield never equals the theoretical yield. That's an easy calculation to do. Well, now we can append onto the ends of our calculations things like, well, quick calculate the actual yield or the theoretical yield or the percent yield as an independent calculation that goes into these strings. So in chemistry, kind of compartmentalize your calculations so you can identify the ones that are screwing you up. For example, it's fairly common for people to stumble on the mole ratio thing. Like, here's a chemical equation, and you can convert the number of moles of A to moles of C using that mole ratio. That one's commonly something that people are like, I don't quite get that one. I can calculate molar mass, that's no big deal. I can convert from moles to grams and grams to mole, that's no big deal. But this ratio stuff is messing with me. If that's you, just isolate it and attack that one thing. Spend your time worrying about that. If you can't diagnose which type of calculation is messing you up at the end, go talk to somebody. Come talk to me, come talk to Shannon, turn to your neighbor next door. But the troubles aren't going to go away. You will not be able to proceed in chemistry without knowing how to do this. So just that's like, I know I'm like all OCD about that, but I see it happen where people think, we're going to start studying bats pretty soon here. No, we aren't going to study bats or bicycles or Oompa Loompas or whatever. We're going to be using moles and calculating gram quantities for moles, balancing equations, etc. See you in lab. Except some of you.